Hello, Math Studies students, and welcome back to another lesson on the Introduction to Calculus. Calculus is a super useful branch of mathematics because it's all about the mathematics of change and has many different kind of functions that it can work with. Well, the work that you had recently, you were analyzing some derivatives and seeing what kind of patterns you saw. And we're just going to take a look at one of them. We'll take a look at the big long quartic, which was 3x to the fourth minus 2x cubed plus x squared plus 3. And the derivative of that happened to be 12x cubed minus 6x squared plus 2x. And you were asked to look for some patterns. And I hope one of the patterns that you noticed was that the two coefficients at the beginning, that the original function had a 3x to the fourth, and the derivative had a 12x cubed. And the original function had a minus 2x cubed, and the derivative was minus 6x squared. That in both cases you notice that the degree of those terms comes down 1, but also that the coefficient and the old exponent get multiplied together. So the new coefficient is a product of the old coefficient and the old exponent. And the new exponent is one lower than the old exponent. That particular thing is called the power rule. And that's kind of exciting. We're going to use that a little bit in the project that we're going to do right now, which is to take a look at this video going on right here of this scenario. Pretty fun stuff. Okay, well that was cute. So let's take a look at this problem in the abstract now. The idea here is that this balloon is rising, actually it's not really abstract, this is a very specific problem. This balloon is rising at 5 feet per second, and the bicycle is traveling 10 feet per second. And the question is, at the moment the bike is right below the balloon is 15 feet high. And the question is, exactly 3 seconds later, how fast is the distance between the balloon and the bike growing? So this particular assignment is going to break down into a couple of different parts. And what I would like you to do is to pause right now, try to sketch this problem out and work on it. Alrighty? And then you can unpause and see a solution, and then your job is to write about how the work you did compares to the solution that you saw. Okay? So, to solve this problem, what we want to do is realize that because the bike was directly below the balloon's going straight up, and the bike's going straight sideways, that we have a right triangle that's getting built here. And the hypotenuse of this right triangle is the thing we're actually talking about. Now, interestingly, in this problem, what we're going to do is we're going to differentiate a bunch of stuff, but we're going to do it with respect to time. And this is called a related rates problem, because the two rates we're talking about, the rate of the balloon and the rate of the bike, have some relationship between them, and therefore the rate at which the hypotenuse is growing is going to be something we can figure out. So what we're going to do is take the idea of the Pythagorean theorem here, and what we're going to do is we're going to call this horizontal distance here B, we're going to call the height A, and we're going to call the distance between those two things C, and we know that A squared plus B squared equals C squared. Well, if we decide to differentiate the Pythagorean theorem with respect to time, what that's going to give us, actually there might be some notation you want to know on this. Delta x over delta, or delta y over delta x for slope is very useful, but that's when there's big changes involved. To make them really small, we go with a small letter d, and we talk about dy dx, and that's another way of talking about a derivative. So we can have f prime of x, we can have y prime, and we can have dy dx, and those are really the three main notations that are used for that. We're going to use that dy dx structure for this. However, we're not differentiating with respect to x. In fact, we don't even have an x and a y in this problem. We've got an a, a b, and a c. So what we're going to do is we're going to differentiate everything with respect to time. And another rule you might want to know is that the derivative of a sum is the sum of the derivatives. So when we have a squared plus b squared equals c squared, when we differentiate that with respect to time, that 2 on the square term is going to come up front, and we're going to get 2a dA dt plus 2b dB dt equals 2c dC dt. Now there's 3 2's in here. We can just cancel all those out, and we're left with a dA dt plus b dB dt equals c dC dt. The question we're being asked to find is, or we're trying to answer, is how fast is c growing with respect to time? So we're trying to solve for dc dt. We know everything else because we know the Pythagorean theorem. We know when this thing was 15 feet high, that 3 seconds later at, was that supposed to be 25 feet high? It was supposed to be 25 feet high. Yeah. Let's take a look at it again. Yep, that was 25, wasn't it? Yeah. So if it was 25 feet high, 3 seconds later at 5 feet per second, it's 15 seconds higher. That's 40 feet. The bike was going 10 feet per second, and so the bike has traveled 30 feet. So we have 30 and 40. I think you probably see a Pythagorean triple here. That hypotenuse is 50 feet, right? So what we do now is we have 30, let's do the height here, 40 times 5 feet per second plus 30 times 10 feet per second equals 50 times how many feet per second? Well, 40 times 5 is 200, 30 times 10 is 300, 200 plus 300 is 500, divide both sides by 50, and you're left with 10 feet per second. Interestingly, at this particular moment, the balloon and the bicyclist are moving away from each other just as fast as the bicyclist is moving horizontally. As this problem goes on, that distance is going to grow faster because that balloon is continuing to rise. So what happened was, up until that moment, the distance between the balloon and the cyclist was slower than 10 feet per second. Then it's going to be higher then, but at this moment it was 10 feet per second. So that was a related rates problem, and I hope you had fun doing it, and your job is to write that up and, basically assess your own thought process in this. Assess your own thought process on this. Thank you. Have a great day.